And welcome everybody to the RISC-V Seattle Meetup. Now the first virtual meetup that we've had in the RISC-V community. Today is April 2nd, and this will be Imperas and Andes Technologies presenting on the RISC-V P-extension and V-extension and custom instructions. And I'm going to introduce the speakers one by one so we can learn who they are, what they'll be talking about. Gordon, would you like to go first?
Sure, I'm Gordon Churchill. I started the Seattle RISC-V Meetup. Really glad to see all the participants here and everybody that signed up and eager to learn more about these wonderful technologies. And we'll be hearing some questions in between the sessions, and we're talking about a coffee break in between sessions as well. So if you have questions, please forward those on to the channel, and we'll try and answer those by typing, and we'll let the presenters do their presentation. Again, thanks everybody for joining this, and we're really looking forward to figuring out this process so that you guys get the best experience possible.
Definitely. How about Larry?
Hi, I'm Larry Lapidus. I'm with Imperas Software, and I'll be talking tonight about RISC-V models for a variety of use cases: architecture analysis, software development, and also design verification. And just so people can locate me, I'm in the San Francisco Bay Area.
Sounds good. How about Charlie?
Hey, good evening, everybody. My name is Charlie Chen. I'm also based in the Bay Area. And this evening, I will be talking about mostly on the V extension for the vector and the custom extension with respect to applications that requires a lot of matrix manipulations, namely AI, AR, VR. So looking forward to that conversation.
Okay, sounds good. So I want to go over the controls a little bit, since this is our first virtual event. Along the bottom of your screen, you should have a participants box that'll show you all the other participants. I don't remember whether it shows panelists or not. You will have the ability to raise your hand. There should be a hand raising thing. And if you do raise your hand, I can reach out to you privately to answer a question. Or if you do have a question, you can also type it into the question and answer box, and it'll come up over on our screens. With that, one thing we talked about is going over the agenda. The agenda tonight will be doing a short video from Callista that explains a little bit about RISC-V. I don't think that with this crowd it'll be anything new. Then we'll jump into, I believe, is it Larry talking first?
No, Charlie first.
Charlie will be talking first about the V extension. So Let me see if I can get the video working, and we'll get started on that.
Jeff, I think there's no audio.
Yeah.
Okay, sounds like the audio is not working for some reason. I apologize for that. We'll have to do some, oh wait. Let's try that.
Excited to share with you the journey that RISC-V has been on, where we came from and where we're headed. I'm Callista Redmond, CEO of RISC-V. So Why is having an open ISA so critical for our industry? Well, let's take a short stroll back in time. The 1980s saw the first semiconductor battle between various ISAs, various instruction sets and architectures that really drove down to one key criteria: power. You needed a constant supply of energy, you needed to have performance, but the demands on that energy consumption required a plug into the wall at all times. Now we've moved into cell phones and other implementations for chips. ARM really took hold on the cell phone revolution, and then we moved forward. Up until now, we haven't had the same drive and the same need for truly open source custom processing, but custom processing has come to our age. We have seen the barriers to entry much lower than they've ever been in the past, and our demands for compute technology require custom open source processing. Where do we see this? We see this across a huge spectrum, from embedded to HPC. We see this in automotive, we see this in cloud, we see this in IoT, AI. We see this across a huge spectrum, where getting down to the very core and adding the extensions and other implementation types critical to your workload are more important now than ever. But our community isn't just single-sided. We have a diverse set of interests, many stakeholders in our community. If you think of a village, everyone brings about their expertise and brings it together for a long-term strategic and sustainable growth. That is absolutely critical. We can no longer rely on a single supplier, a single vendor, a single partner, or a single customer to meet our business needs, to grow and profit for the long term. So this brings about a key criteria for business survivability and sustainability today. You have to have a diverse set of innovation partners and a diverse set in your supply chain, no vendor lock-in. And that allows you to have a much broader addressable market. So the more partners and the more suppliers you can bring brings greater competition and greater option and choice into who you collaborate with, while again expanding your market opportunity. That market opportunity may be geographic, or it may be working on adjacent spaces, adjacent industries to where you began. That allows for growth, long-term sustainability. We're very active around the world. In China, we're seeing great growth around 4 different associations that we partner with. They're looking at academic, they're looking at research, they're looking at industry and venture capital. In China, as well as around the world, RISC-V is a great option, whether you're a startup or a large multinational. We've got room to innovate and grow for everyone. In Europe, the European Processor Initiative has adopted RISC-V for acceleration. This is critical in HPC, which leads us straight into artificial intelligence. At Embedded World, we're seeing it deployed readily across many different types of implementations in the embedded space, industrial, IoT, you name it. There's not one corner reserved for RISC-V, but a broad opportunity. In India, the Shakti project, 6 different processors based on RISC-V. This is an initiative that is truly global with global collaboration. In Japan, Japan is looking at RISC-V not only for traditional enterprise space, but also in automotive. We're seeing great advances in automotive also for safety and security. In North America, you see proliferation of RISC-V across a wide variety of participants and stakeholders, from large multinationals to very small startups. In fact, one of our most successful startups, Sci-Fi, is based completely on RISC-V, and their growth and presence around the world is known by many. In Pakistan, Pakistan wants to be part of the technical revolution as well. And last year, we saw more than 3,000 people come together in 2 different city events to support RISC-V in fact, making it their national architecture. This is something that's so important to us, to have public-private support for RISC-V. This means allowing RISC-V and supporting RISC-V in universities for students, enabling communities and connectivity between engineers to collaborate within local regions, as well as supporting businesses who commercialize RISC-V, whether that's through innovative incubation labs or through other types of incentives that the public sector can offer. So join the RISC-V revolution. We are an organization that provides support across a wide variety of needs that all sizes of our companies need. In fact, we are bringing together more than 530 different members today. That's around the world. We have about nearly 60 members in Europe alone. So how is this growth coming together? As I mentioned, it's not just geographic, but it's across a wide variety of interests. These interests span from tools and custom IP to processors and implementations used in-house. These 6 programs are things that our organization, that RISC-V, provides to all of our members. These are critical to everyone's success and critical to our forward progress. So first, we have technical deliverables. We have more than 25 different work groups and committees that are focused on various implementations, various extensions, and things to make RISC-V easier to customize. We have verification and compliance. We just rolled out our first compliance suite to allow folks to really truly comply to the base ISA spec. Visibility. Visibility is not just about what our organization is doing, but it's about the ongoing success and visibility of what all of our members are doing. So that is something that we are here to help amplify through press and analyst relations, through events, through blogs, through videos, and many other ways to ensure the visibility of RISC-V and all the success of our members. We are also working on learning and talent. This comes in 2 flavors. One, we have nearly 30 different offerings from universities, very key to spreading university adoption of RISC-V in their courses and in their research. And second, across professional training and development. We've launched a program that will bring together all the great content about learning about RISC-V as well as deep dive topics to provide to our global community through online courses. Advocacy and outreach. This is a new area that has come into popularity lately called developer advocacy. I assure you, this is not about marketing to engineers. This is about connecting engineers to engineers through more than 2,500 members of our meetup community in 25 different cities around the world. It's about creating online forums for engagement, posting a challenge, receiving lots of feedback and ideas on how others have tackled those same challenges. This week we launched a RISC-V Ambassador program. If you're keen to be a RISC-V ambassador, please let me know. And then finally, Marketplace. Marketplace is critical. This is where we play ultimate matchmaking. Here are all the RISC-V things available today if you're looking for something. Today we have around 89 different cores and SoCs, and we have 94 different software, tools, and other resources listed up on our website. We're working to refine this and grow this. We're going for scale. So I hope you'll join the revolution. I hope you'll sign up for RISC-V, learn more, and join us in this new frontier. Thank you.
All righty. So I suggest we dive right into Charlie's talk after this.
Okay, we'll do. I'm going to try to share now.
Okay.
Hi, everybody. Can you hear me okay?
Yes.
Okay, good. So tonight I'm going to talk about the custom extensions and vector extensions. As Calista says that, this is an open instruction set architecture. And so where at least Andy sees strong momentum for RISC-V within the last year or so really is in this market that focus on real time and performance in the area of computing. And so I'm going to go through that, and I think Larry will talk about the extensions as well and how to model that. So just a quick on Andes, probably we are the oldest and most, the earliest of the processor companies supporting RISC-V. In fact, we've been around for 10 years before RISC-V, the community was formed, with R&D both in Taiwan and in the United States, in California and Oregon. So the way we have observed the RISC-V market is that when it got started, the first most important and rapid adoption socket is in the cost reduction of ARM sockets, in deeply embedded markets, and also in FinFET SoCs, where because mass cost is so expensive, a lot of finite state machines got replaced by microsequencers that are based on RISC-V instruction set. So that orange box really got filled up quickly, initially with open source RISC processors, and then dedicated RISC processor vendors like Andes. And recently, even semiconductor companies themselves are developing their own RISC-V processors. And just in my personal opinion, RISC-Vs have not been very successful, and certainly, in my opinion, not ready, are sort of the shrink wrap microcontrollers, vis-a-vis NXP, Renesas of the type, because the ecosystem just is a little too fragmented to be handing products to distributors, and it certainly is not mature enough to tackle phones, tablets, server. And so where Andes has seen a lot of focus and interest on is real time and performance. One of them is bringing accelerators closer to the CPUs, so that CPUs are not just merely memory mapped I/O devices that are really far away that you program, as in the ARM and PowerPCs and before that MIPS architectures, but something that you can actually program directly as like a coprocessor or instruction extensions. And second thing would be, using vector process, extension to address not the inner loops and the kernels, but the in-between layers of the workload for AI, AR, VR, and computer visions. And we've seen a lot of interest in that. And it certainly has brought a lot of challenges that force, all participants in RISC-V to work together, including the likes of Imperas, Synopsys, Ultrasoc of the world. And the last part of it is, how to move data efficiently in these real-time and high-performance applications. So tonight I'll talk mostly about these 3 points. So, if we look at those applications that are in real-time high performance, the challenge is always for the software guys, they would love the efficiency of something like a TPU, tensor processor from Google initially. So Google pioneered this architecture where it's just one big array of multipliers. Super efficient, but super inflexible, both in terms of operations could do and also the data movement. And on the other hand, obviously, there's the tried and true x86 processors where you can do anything you want. And it's actually really super powerful if you have 100 watts of power supply to do it. So most of the effort that we've seen in the last year and a half through a number of startups as well as established companies is to combine the flexibility of x86 or a RISC processor in this case, and an accelerator that can handle very specific tasks. And if you think about the accelerators, you could program those as RISC-V instruction extensions, but probably there's a different way, there's a better way to do it, because an instruction extension could potentially lock your processor up so your processor can't do much. And potentially it requires more instruction bits than the 32 bits that RISC-V has. And so, at least from Andes, the way we think about it is that we really ought to treat the accelerator as like an old-fashioned 1990s style, floating point coprocessors. So the coprocessor would have its own instruction set. It's got its own resources and potentially memory. And the instruction set for the coprocessor should contemplate both the scalar RISC-V, resources like cache memories and registers, as well as the coprocessor's own resource, like floating point register or its own register files and its own memory. And, as I mentioned earlier, a lot of accelerators have very specific way of moving data. And so when data needs to be reordered, we see RISC-V handling the complicated work of data permutation, sliding, gathering, compressing, expanding the data. And the third is in between layers, there are some kernels where there are some computations that's needed. And so we see RISC-V's vector processor, vector extension to be very flexible in helping to address that need. So in this slide, just talk about sort of what you would think about if you want to treat the accelerator as a coprocessor. So a coprocessor, it needs instruction, and the simpler the accelerator, the wider the instruction needs to be, because essentially the decoding of the syntax have to all be done by the RISC processor. So it's sort of a fire and forget kind of thing, that where accelerator already has the decoded microcode to just execute. So one of our licensees actually has, something like a 256 or 300 bits of instructions that it sends to the accelerator. So you send it, go fire, and you forget about the accelerator until it's done. And the accelerator should be able to tell the RISC-V processor that, hey, I'm really busy, and you have to stall and wait for my computations to all be done before you give me more tasks to do. And when that happens, the RISC processor would be, waiting for the accelerator to be ready. So, so the instruction semantics for the coprocessor will need to contemplate for the wait for ready semantics. And the third is the coprocessor accelerator needs data, needs to load data and needs to store data. So loads and stores and reformat of the data will be sort of an important constructs that the RISC-V instruction extension must contemplate. Now, traditionally, RISC-V instruction extension, dating all the way back from UC Berkeley, has been used, using this concept called ROC. And ROC is very generic and very high level. It's a transaction model. But, if you look at this, while it can be done with a transaction model, the transaction model just doesn't quite have enough signaling capability to contemplate all this. And so what we have done is to add all this thing into the processor extension so that you can write essentially system C Verilog to include the operand and to include the high-level meaning of the instruction and use a tool to automatically generate compiler, assembler, debugger, extensions, and add the extension to the instruction set simulator and connect the RTL database to the scalar processor, RISC-V processor core. And so all that sort of is automated. But the main point here is that in this world where the accelerator is connected to the RISC-V instruction extension, you can think of ways to bring the accelerator closer to the RISC-V processor so they can be more efficient with lower latency and higher throughput. And where there's in-between layers and there's vector computation that's needed, we have gone ahead and developed, and we actually shipped the very first completed RISC-V vector engine in January of this year to our first customer. It uses the RISC-V vector extension, 0.8 draft of the spec, and it's got some AI optimization in it, in that it supports bfloat 16, and it actually supports 4-bit integers for efficiently storing the weight of the algorithm. And it's sort of a testament of how efficient the RISC-V vector extension is. The implementation at 1 gigahertz in TSMC 7 nanometer is only, it's less than 0.3 millimeter square in the worst case corner. What the RISC-V vector spec is really good at is allow the user to configure the system. So the vector length, so this is the length of your register file. It actually is not 64-bit or 128-bit, fixed like a neon, if you will. It's scalable at design time to be as short as you want, but logically maybe 128 is as short as you want. But it can go as high as 1024 or even higher, depending on your application and your power budget. The second thing which the vector extension actually allows for, but doesn't explicitly say that you can actually have multiple ALUs. And depending on the microarchitecture of the processor, you can actually go into multiple issues, multiple pipelining and chaining capability. And we've done exactly that. And I'll show an example in the next slide. Now, to get to where the edge AI applications or the IoT AI application needs to be, or AR, VR glasses, low power is really important. And the instruction set per se does not have any, power concept of power management, but we've implemented so that you can multiple levels of clock gating, and you can definitely think of a vector processor engine, locking away some processing units when the instruction is not using. So, and the whole thing is synthesizable, in order, single memory, cell-based, so it's very simple to implement. The table below and to the left is a kind of an interesting table in that it basically says that to make it appealing and sort of power and performance optimized for low power AI, AR, VR, computer vision applications, we've only implemented unit low store architecture for vector load store. And in the next slide, so I'll talk about why. So the RISC-V vector instruction set truly is very broad. And So it actually contemplates applications such as high performance computing, like computational fluid dynamics, if you will. So the 64-bit architecture, floating point instruction is supported, but in this application, it's just not very useful. So we actually have not implemented 64-bit. And so this is a bit of an eye chart, but basically it says that if you have to reorder your matrix, or you have to load in the data that are skipping, every 3, every 4, depending on your vector indices, the way you could do it is you can load the entire array into the vector register file, which you can define to be very big, and you can use the permutation instructions. And in this slide, I've used vgather instructions to reorder the data within the matrix, so that once it's reordered, you can either use the vector instructions in RISC-V to do multiply, accumulate, or you can send the reordered data out to the accelerator to compute. Either way, the key point here is that you use simple cache memories or flat memory, and you load the entire matrix inside the vector engine and use the vector engine to manipulate the data. And I thought for the RISC-V instruction set, it's a really powerful way to get high performance and low power. And this is the last slide, I believe. It just talked about, well, with that, what you really want to do is preserve the memory bandwidth. So we have, cache write around, instruction data prefetch, having data coming back out of order, and having data and instructions split out various different ways so that the memory can keep up with the vector processor. And just to summarize, we have seen at the Andes in the last 15 to 18 months, 15 months, a lot of adoptions, a lot of interest in the purple box, in the high performance real-time application where we bring the accelerators closer to the CPU. We enable a very powerful vector processor extension, and we allow for very efficient memory transfers as well as data manipulations inside the vector processor. And I believe that's my last slide.
Okay, sounds good. There are a couple questions coming in. Drew has asked a couple questions. One is there compiler support for the RISC-V vector extension?
So there is no, not compiler support per se, but in GCC and LLVM, they both have ways for kernels to be developed using what's called the intrinsic functions. And these are symbolic intrinsic functions. So, when you write the kernel code, you can actually reference by name and not by the register numbers. And then the compiler backend would actually do the register allocation as a backend optimization. So I thought, from way back when we had to code DSP, inner loops in explicit registers, which was painful. I thought that was a really, really nice way to do it. But to get back to your question, compiler support today is not really available yet.
Okay. The next question, what are some use cases for the vector extension, such as machine learning or media codecs?
Yeah, so I would say the vector processor, as good as it is, will not likely be used as the sole computational engine for AI, machine learning, computer vision, and other inferencing or even learning algorithms. What it's very good at is it's very good at managing the accelerator and providing the computational flexibility for massaging the data or doing the in-between layers and doing some heavy computations, but supporting the accelerator.
Okay, great. One more question coming in. Charlie mentioned clock gating to lower the power in the accelerator. Interested to know how clock gating works. Do you have any benchmarks to show how much the clock gating can lower power for specific applications?
Yeah. So in applications like polling, which is a pretty generic but important learning applications, polling algorithms use very specific instructions and use a lot of them, but it doesn't use a lot of the multiply, for example. So in those instances, the clock gating will gate off the the multipliers, both floating point and integer. And we've achieved like 80% power saving. So that's just one example. And there are other examples of basically instruction level clock gating that we clock gate off any AOU that's not used by that particular instruction. And depending on the workload, we've seen saving of as little as 30%, but as high as 90% on a per instruction basis. So I would say clock gating for when the vector processor is running, it's easily in the 40 to 60% power saving range. And in the overall, compute time, when you include the time when the vector processor is not running, I think the power saving is tremendous. It's more like an 80, 90%.
Okay, great. Got a number of other questions coming in. One is, can we examine the System C or TLM models that we can test?
Yeah. So I didn't go through that in detail. The tool, which is called COPILOT, is actually installed at the licensee site. The whole thing is automated, and the licensees themselves actually write the System C model and the instructions. We are just providing the tools to automate that.
Okay.
Yeah.
Another person says, I'm interested in hardware, software, code design or co-design issues like COPILOT or QEMU.
Yeah. So we don't per se, provide high-level trade-off tools. There are a lot of companies that do much better than that. What I will say, though, is that when the software gets at the kernel level, and most of our licensees know exactly which kernel is going to be key for their applications, what we have provided is a tool and it's called Clarity. And it basically allows you to peek into the processor at a cycle by cycle basis to look at all the registers, all the resources, and all the pipelines, so you know whether your code is written well or not. And you can optimize your code to make sure there is no, resource contentions or no bubbles in your pipelines. And that's really at the low level. That I wouldn't call that hardware software code design.
Okay. Next one, Andes vector implementation. Which data type is supported? Integer and single, double, floating point?
Yeah, so we support every single data type except for 64-bit floating point. So we support all integer, all floating point. In fact, bfloat16 is also supported on a provisional basis. 4-bit integer, which officially is really not supported, we support it just because it's so important to be able to compress the weight functions in the memory or in the DRAM. And so we support that. But when it's loaded into the VPU, it's either expanded to 8 or 16-bit. So it's stored as 4-bit, right? It's expanded into 8 to 16-bit during compute time.
Okay, excellent. Drew asks, Charlie mentioned the NX27. Is this the 27 series CPU that is Linux capable?
So it is, the only thing I would say though is that the vector memory is assumed to be within the TLB entries. So because of the way the exception is handled in virtual memory, right now our vector processor anyway does not assume that you could take a page fault in Linux if you are running the processor in the virtual memory.
Mm. Okay.
So sort of a real-time appendage to a Linux environment, if you will.
Okay. Drew, I hope that answers your question. Marnie says, thanks, it's impressive. And it looks like we've got one more question that's being answered on the chat about running an RTOS.
Yeah, thanks, Marnie.
And it looks like Larry has answered yes, you can run RTOSs on both the Imperas and on the Andes cores.
Yeah, it is. Thanks, Larry.
Yeah, sure.
So I think, if there are no more questions, I'll transfer back to the host and Larry next.
Okay. I think since we're about halfway through, it might be good for us to take a 5-minute bio break. So maybe we should, we'll pause the recording now. Great. So it's welcome back, everybody. Thank you all for doing this and coming back. I'm going to go ahead and share the results of the poll. Very exciting stuff. Okay. So let's go ahead and get started again. And I think Larry is up next.
Yeah.
Oh, wait, we've got one quick question let's answer beforehand. May I know the difference between open source and open ISA? That's an excellent question. I thought we could maybe take a minute to answer. Does one of the panelists want to try that?
Oh, sure. So this is Larry. The open ISA for RISC-V is not so much open source as it is an open standard. There is no source code that the RISC-V Foundation is providing. There's a specification for the RISC-V instruction set architecture. So this is in contrast to open source software where you do actually get source code. So that's a simple answer, but hopefully to the point for this.
So I think of open source as a peer review, open contribution, open instruction set allows customers to add instructions to it. They are different, as Larry said. Yeah.
Yes, I tend to think of the open source in this context as being part of the process.
Yeah.
With the result being an open ISA that has its own license. So it's a similar process to open source, but it's not open source in the sense that if you did a tape out, for example, that was open, or if you had literally a set of open code that you could then print.
Yeah.
That's a different sort. That's a different process. So, and in fact, Drew has mentioned on the chat that he's moderating a quantum computing course on Sunday for Hackaday. So I wonder if maybe Drew might actually cover open source and open hardware on that. So with that said, I'm going to call the questions, and let's go ahead and hear from Larry about models for architecture analysis.
Okay, well, thanks, Jeffro, and thanks everybody for attending. Interesting times for everyone right now, and so I hope this format is going to prove to be valuable to everyone, and provide a way over the next weeks and hopefully not too many months for us all to get together and share information and talk about RISC-V. So let me provide a bit of background on Imperas to start with, and just talking about what we're doing. We started the company thinking or with a position that nobody builds a chip without simulation, and similarly, nobody should develop embedded software without simulation. So that's where we're starting from. We develop simulators, tools, and debuggers and models, especially processor models, to help embedded system developers get their software running and hardware developers get their designs correct. We've been around for more than 10 years. We're self-funded. There's no outside funding. We're profitable. We're based in the UK. Team's got a lot of EDA background. And we've got 2 websites, and I'll be talking about the Imperas tools, but I will also talk about Open Virtual Platforms, which is the website where we put our processor models, our platform models. And this is part of our, at Imperas, our hybrid strategy of providing open source models with commercial tools. So I thought maybe a bit of background about Imperas and our experience with RISC-V might be worthwhile here, because we've been looking at RISC-V for going on 4 years now. In June of 2016, there was a talk by Krista Sonovich at the Design Automation Conference where we first learned about RISC-V in person, and our thought was, wow, looks academic, looks fragmented, never going to go anywhere. And then 5 months later at the RISC-V workshop, I don't remember what number the workshop was, but November of 2016, there were 350 attendees from some serious companies, including Google hosting the workshop. And the ISA looked to be converging at that point. And so we said, okay, time to take a more serious look at this. We joined the RISC-V Foundation in Q1 of 2017, built our first processor model. We started participating in the compliance working group shortly thereafter. We introduced a methodology for adding and optimizing custom instructions for RISC-V cores. It took a while to actually get our first paying customer, because I think a lot of people were trying to figure out what is RISC-V, and do we want to do anything more past a proof of concept. But actually, starting with that first paying customer, we have seen real projects, more than just proof of concept, more than just the little real-time 32-bit processors that do the housekeeping on chips. We've seen real projects, as Charlie was talking about, and certainly we share customers with Andes, including that first customer using the Andes vector instructions. So we're seeing serious use now of RISC-V. We've also moved past compliance, and we're working on DV flows, design verification flows, collaborating with Google on their open source instruction stream generator. We've participated in other organizations. And so we've been just ramping up our RISC-V support here. And the result was for us that in 2019, our RISC-V related revenue was 4 times our ARM related revenue. So as a real metric of the growth and adoption of RISC-V, for us, that was pretty darn significant. And I think it speaks to the fact that, that we are now past the proof of concept stage with RISC-V and seeing real commercial projects, seeing commercial silicon that's based on RISC-V. the customer use cases that I'm going to talk about here in general are architecture analysis, especially custom instructions. I'll talk just briefly about software development, debug and test, and then processor and SoC verification. So before I get into that, I just wanted to provide a bit of background information on the processor models and virtual platforms and tools. So what we're doing is building instruction accurate models of the processors. And this is just a generic block diagram here. But essentially, if it involves the functionality of the processor, then we model it. If it's something having to do with microarchitecture and the implementation details, if it's something that a software developer doesn't worry about, then we don't worry about it either. So we don't care what the pipeline is. We do care about the full instruction set. You can do things like cache in these models. We build the models in C, but they also have a native System C TLM2 interface, and so you can use them in that environment as well. The models are available under the Apache 2.0 open source license. Models require an Imperas simulator license to run. For RISC-V, we have models of both the generic RISC-V specification, so 32, 64-bit RISC-V with all the various alphabet of extensions. We've added the vector and bit manipulation instructions as soon as the spec stabilized. And in fact, we were the first simulator, first model to support both those instruction extensions. We support the Andes cores, the 25 series, and now the new 27 series, including that NX27B with the vector instructions. Now, it's also easy to add custom instructions. The user can do that, Imperas can do that. While we do provide the processor models as open source, we have a flow for adding the custom instructions that involves putting them in a side file so as not to perturb the verified model. And I'll talk a bit more about where the, or what that methodology is for custom instructions. In addition to the processor models, we also have models of peripherals. These range from simple things like interrupt controllers and timers and UARTs to DMAs and USB and Ethernet. So we handle a whole bunch of things. We've got hundreds of models in the library. The models, again, are all open source. You can go in and modify those as needed. And then models get put together into platforms. And so here we've got a very simple block diagram using an Andes N25 and RB32 core running FreeRTOS. Yes, you can run an RTOS on the models here. You run the same FreeRTOS that would run on the actual hardware. And so with the extendable platform kit, you have a known good starting point running the FreeRTOS or running Linux. And then you can add peripheral models so that you can extend the platform, thus extendable platform kit, to be a model of your own SoC. And then just a brief view of the Imperas environment here. There are the models in the virtual platform. There's a just-in-time simulator engine that is quite fast, billions of instructions per second. And then tools, what we call verification, analysis, and profiling tools. and then multiprocessor, multi-core debugger. And certainly the simulator can work with GDB, it can work with third-party debuggers, for example, IAR and Lauterbach, but it's working here also with the Imperas debugger, which provides some additional features. I won't worry about that tonight. On the customer use case side, one of the key things is custom instructions and architecture analysis. So if we think about how processor performance is optimized, there are a few sort of standard things as you're working with processors, irrespective of RISC-V. You can move to multi-core, you can optimize the pipeline, you can improve the memory usage or memory latency. But something that is, I think, more or less unique to RISC-V is the ability to add custom instructions really for application or domain optimization. And interestingly enough, the things that we usually see custom instructions used for actually is to improve memory usage and memory latency. So RISC-V is providing some additional capabilities for processor and SoC architects to actually improve their performance. There is this flow that we have for adding new custom instructions. Again, most of the time what we're seeing in RISC-V is to add custom instructions to optimize a specific application or a set of applications in a domain. And so you want to go and characterize the C application that you're using, then develop the new custom instructions, and then recharacterize the application. And so just having a look at that, this first part, characterizing the C application, again, using the Imperas instruction accurate simulation. And here we're just cross-compiling something to an RV32IM. In this case, the example uses a character stream encoder, the CHA-20 encryption algorithm. And we've just gone ahead and run this just to get our baseline. And just from a performance perspective, hard to see here, but we're running over 1 billion instructions per second on a standard PC. And then the next step in this is that iterative loop of developing the custom instructions and then characterizing those instructions. And so now we've gone back, and I've skipped a few steps here, but we're running essentially the same instruction accurate simulation, but now we've added timing annotation and we've added in the custom instructions. So we've added in not just the custom instructions to the model, but we've actually added in timing information for those custom instructions. And we've gone and simulated all that together. And in this case, for that CHA-20 encoding, we've gone from 16.59 seconds down to 9.21 seconds with those custom instructions. So, yep, we have seen some improvement there. It's not just running the timing estimation, though. You also want to do things like look at function profiling. And so originally, without the custom instructions, this process line function was the key bottleneck from a profiling perspective. And now we've reduced the percentage of time in process line from 21% down to 16%. So pretty significant reduction there. In this environment also, as you add the custom instructions, you still want to be able to use all the tools that are at your disposal. And so things like the debugger so the new custom instructions, any new additional state registers, these are all available in the debugger, and then tools like tracing of disassembly. Again, this is also available without doing anything more except adding those custom instructions to the RISC-V processor model. So architecture analysis and then adding custom instructions is first use case. Software development, debug, and test is the second. Nagravision in Switzerland is one of our customers. They build devices that protect streaming video. They also build IoT devices. They're using RISC-V. They build their own peripheral models for the proprietary pieces in their SoC, or they use modified models from the OVP library. They're using the Imperas tools, both for debug and the analysis tools. And these guys have a full agile continuous integration methodology, including that continuous integration testing environment. And certainly what they're doing, especially on the streaming video side of things, is worrying about security. And that's actually one of the areas that we see RISC-V being quite strong in, is being used for security applications. And then the last thing is processor and SoC verification. So one thing I wanted to just be clear about here, without going into a lot of detail, but compliance is not verification. So there are compliance tests that are available from the RISC-V Foundation. Imperas has been quite involved in the compliance working group, and actually pretty much everything on the RISC-V compliance GitHub repository is from Imperas. What's up there on that GitHub repository are the compliance tests. There's a compliance framework, and there's also a free version of the Imperas tools, this RISC-V ISS or RISC-V OVP Sim ISS, which can be used as a reference model for compliance testing. So again, you can go to these GitHub sites, you can download the compliance test suites, you can download as part of that the RISC-V OVP Sim. It's a reference simulator. It's all available for use at no charge. Imperas does a bunch of things in addition to RISC-V OVP Sim, the support for custom instructions. You know, if you're getting a core from Andes, it's going to be quite well verified. Actually, of everything that we've tested, Andes has the highest quality IP, the highest quality silicon coming from that IP. But if you're adding custom instructions, you want to do some additional verification there. If you're building your own RISC-V processor, we see everyone that is doing that using the Google instruction stream generator. And we've been working with Google to improve this flow. There's also, with the instruction stream generator, the Google instruction stream generator, it uses a trace compare methodology. That's a little bit awkward as you get to more complex instructions, more complex processors. Step and compare methodology would be much more efficient. And so we're working to add that in. And we've also developed a vector test suite to help people that are building their own implementation of the vector tests, because the vector tests in themselves are as complex as the rest of the RISC-V instruction set. I'm out of time here, so I'm going to leave this slide for you to view on the video, talking about the instruction stream generator flow, and also about the step and compare methodology and the encapsulation of the Imperas OVP model there. So what we're seeing here is that our users are benefiting from improved system quality, from reduced schedules and costs by using these models, using the Imperas methodology and know-how. So thanks very much for your time. And as I said, we've got the two websites, the Imperas website and the Open Virtual Platforms website, where you can get more information on our support for RISC-V. Thank you.
That's great, Larry. Thank you. There's a few questions if you have some time to answer.
Sure.
One is about design space exploration method with Imperas tools. I don't know if you have if you're familiar with that.
I'm not sure exactly what's meant by design space exploration here. What in the flow that I showed, what we can provide is a way to look at custom instructions. You can also actually, with or without custom instructions, there's that timing estimation capability. So there is the potential for looking at different parameters and different ways of working with this. And because you're building models of the hardware as well as the software, you could do trade-offs between implementing some things as hardware or software. So I hope that answered the question.
So as well. So the next one is from Drew. It says, with Imperas, could one do something like model Linux running on the open hardware Core V chassis SoC, which includes NXP USB peripherals? So would it make it possible to work on Linux kernel drivers, for example, from peripherals like the USB controller before the SoC is fabricated?
That's one of the common use cases for our customers into it. One is porting and bring up of the operating systems, and then the second is the the follow-on to that, which is to build the drivers and test those drivers. So absolutely, Drew.
Okay. Next one's actually from Gordon. It says, can you talk a little bit about whether the Imperas models support Andes processors? I think you may have covered that on your last slide. With vector instructions now, or is it a plan for a future update?
So thanks, Gordon. We do support, I think, all of the Andes cores. We do have models for all the Andes cores, including the cores with the vector instructions. As I think I mentioned, one of our joint customers is that first customer using those vector instructions. This is actually a really cool design. We're excited to be collaborating with Andes and with this customer on this design, which I think is really pushing barriers, pushing the leading edge of all of our capabilities. So yeah, we certainly support Andes cores and specifically the vector instructions.
Great. So Shivam says, great presentation. I wanted to know, how does support for designs work? You mentioned that Sci5 and Andes are supported. Can we use this tool in an academic design?
We have people going to the OVP website, the Open Virtual Platforms website, on a daily basis and registering from the academic community to use the simple simulator and models that are available from Open Virtual Platforms. On top of that, for groups that are doing courses, for professors that are doing courses or for research groups in the academic world, we provide free access to the full set of Imperas tools. We have somewhere north of 50 universities worldwide using those tools. Not all of that is RISC-V. Actually, I'm not even sure what the percentage is that is RISC-V now, but absolutely you can use the Imperas tools in academic designs.
That's great. I've got one from Camilo. I want to ask, do you use formal tools for processor verification?
No, we do not. That's a good question, Camilo. How do we verify our processor models, and how do you trust those? So right now, Imperas has models not just of RISC-V, but also of the full set of ARM cores, MIPS cores, Renaissance, PowerPC, ARC, the Xilinx Microblaze, the Altera Neos 2. We've got around 250 different processor models in the Open Virtual Platforms library. We work very hard on building test suites for those processor models and testing those. Internally, we actually have a continuous integration methodology where our developers have to run a full suite of our tests. Probably about 12,000 tests are run in less than 10 minutes every time one of our developers checks in code. So we develop our own tests, but in addition to that, we collaborate with every one of the processor IP vendors to validate the processor models. And either that means that we're receiving some test suites or some other technology from the processor IP vendors so that we can test against that, or we're providing our models to that vendor for testing. So we certainly have that sort of a relationship with Andes where we share technology. Actually, it goes both ways there, where we've provided them with our models for testing in their environment. They've provided us with technology so that we can test our models in our offices. So we spend a lot of time on this, but no, we don't use formal tools. But we're pretty confident in the quality of our models.
Sounds good. Got one more from Drew. Are there any of the open peripherals from LibreCores available for simulation in Imperas?
Sorry, Drew, I'm not familiar with LibreCores. We do have a number of peripherals in the library, and it's pretty easy to build new peripheral models. So if that's of interest, we'd be happy to collaborate with you on that.
Oh, he says, like, I'm wondering what is going to take for industry to converge on an open USB controller implementation. And SoC design will no longer have to license Mentor or Synopsys. So
that's a big question. And while it is going on 8:30, I have not had a glass of wine yet. And so I'm not sure I can answer that one. But essentially, it's going to take a lot, Drew, to converge on an open USB controller implementation, because it's a lot of work to build something like that. If people build something like that, they usually want to get paid for it. Or the flip side of that is that if you want to use something like that, you sure as heck want that to be high quality and verified. So I think we're still a little ways from an open hardware implementation of something like USB or Ethernet.
So he's hoping open hardware might be, or yeah, like the open hardware group might be able to do that once the core V designs are proven. Very interesting discussion.
It's something to bring up. Are you, if you're participating in open hardware, Drew, then we'd welcome that sort of input and welcome your participation in open hardware. Right now, I think the first thing in open hardware is working on those core 5 designs and making them production worthy.
Very cool. All right, well, I think we've gone through our questions and I think we're just about done. Gordon, do you want to do some, say a few words?
Yeah, just wanted to give a final thank you again to our speakers, Larry from Imperas and Charlie from Andes. This was kind of put together a little bit at the last moment. We didn't know how we were going to get this material to all of you attendees. Thank you also to all of you attendees. This is actually a worldwide event right now because we've got so many people from various places around the globe. So this is a pretty fantastic showing for our first RISC-V virtual meetup here. So thank you again to everybody. And that's it. That's my lot.
Yeah, thanks very much for organizing it, Gordon. It's great. And thank you, Jeff. And good seeing you, Larry.
Yeah, thanks a lot,
thanks,
Gordon.
Everybody.
And thanks everybody for attending. This was great. Have a good evening.
Yeah, good night.
Thanks, everybody. You too. Have a good one.